Hello everyone, thanks for coming. Today we are going to do a review of our week 5 lecture for our ODE class. Hello everyone, thanks for coming. Today we are going to do a review of our week 5 class for ODE. So first, we introduce methods to solve non-homogeneous linear ODEs. The first method is undetermined coefficients. So this applies to constant coefficient case. So undetermined coefficients basically ask us to assume that a particular solution as a combination of functions or a summation of polynomials, exponential signs, cosines with undetermined coefficients, and then we try to determine the coefficients or constants by substituting this y into the equation. Of course, sometimes our assumptions might fail. In that case, we need to make additional assumptions. The other approach is variation of parameters. So the variation of parameters applies to the case when the coefficients are not constants. Here we assume that we know the fundamental solutions to the homogeneous equation, as in we assume that the solution to the non-homogeneous one takes the form where the coefficients are not constants, the coefficients are functions. We impose several additional conditions to get the equation satisfied by those coefficients ui. In the end, we can get the solution in this form. W is a Wronskian, while Wm is a Wronskian of replacing the original Wronskian with a constant vector in the mth column. We talk about the power series and the power series methods to solve ODEs. So the power series, first we need to know when the power series converges. It converges if the partial summation has a limit as n goes to infinity. We have the absolute convergence, that is, if we take the absolute value of each term as the summation converges, then we call it to converge absolutely. We can do the ratio test. So here, L is the limit as n goes to infinity, the n square root of the absolute value of an. If the ratio test is satisfied, then converges, otherwise not converges. Inconclusive, it's if x minus x0 absolute value times L equals to 1. So we do have the radius of convergence rule. We have absolute convergence if the absolute value of x minus x0 is smaller than rho, and definitely diverges if the absolute value of x minus x0 is greater than rho. Series can be added, subtracted, or multiplied term-wise. So in all calculation, we just need to do the calculation as what we are doing with normal functions. Because series, they are also a kind of functions. Differentiation and integration may be performed term-wise within the ratio of convergence, and that would not change the radius of convergence. The coefficients, if the function for the series is denoted by f, the coefficients an is the nth derivative of f divided by n factorial. Two power series are identical if coefficient for every term is the same. Finally, we can change the index from n to m or I or j or k because it's a dummy variable. And also, the index can be shifted, which will be used for solving ODEs. So first, we look at the homogeneous linear ODEs in this form. We assume that at x0, px0 does not equal to 0. In this case, we can convert this ODE into an ODE whose coefficient in front of the highest order term is 1. We call such x0 to be a singular, an ordinary point, because px0 is not equal to 0. We call x0 to be a singular point if px0 equals to 0. In this case, the coefficients P and Q may be unbounded, and we may need some special techniques to solve it. At an ordinary point, the solution to the second order homogeneous linear ODE exists and is unique, and then we can apply the power series method to solve. Basically, we just plug in this power series into this ODE and then to find the coefficients term by term. We'll introduce this later in our next week's lectures. Thanks for listening.